Welcome, curious minds, to the deep dive. Today we're embarking on a journey through the absolutely fascinating history of physics.
It really is quite a story.
We've taken your sources, everything from ancient philosophical musings right up to cutting-edge quantum ideas.
Yeah, real mix.
And our mission is to extract the most important insights, maybe some surprising facts, and definitely the engaging stories. Think of this as your shortcut, maybe, to being genuinely well-informed about how our understanding of the universe has evolved.
From way back when.
Exactly. From early natural philosophy, all the way to modern quantum mechanics, which is where things get really interesting.
And this deep dive isn't just a history lesson, is it? It's more an exploration of how yesterday's big discoveries really light the way for tomorrow's breakthroughs.
That's a great way to put it.
We'll try to pinpoint those pivotal moments and share some of the inspiring personal tales of the brilliant minds behind them.
Yeah, the human side.
You'll really see how humanity's, relentless curiosity has shaped our view of reality.
Okay, let's unpack this journey then. Starting right at the very beginning. How did the study of the physical world even, begin? Who were the first key figures?
Well, our story really kicks off with Aristotle. Back in 4th century BCE Greece, he was truly groundbreaking because he was the first to actually name this line of study, physics.
He literally wrote the book on it.
He did, and his core belief was that careful observation of physical phenomena could lead to discovering natural laws.
Makes sense. Observation first.
Right. He famously taught that everything was made of just 4 elements: earth, water, air, and fire.
Classical elements.
Exactly. And, to illustrate his view, you can picture him maybe dropping a stone and a feather. He'd say the stone falls faster simply because of its inherent nature, its stoniness.
And that idea stuck around.
Oh, yeah. Surprisingly, it persisted for nearly 2,000 years.
Wow. That's quite a legacy. But of course, knowledge wasn't just in Greece, right? We know scholars in India, China, the Islamic world. They were also making key contributions.
Absolutely, especially in astronomy and mathematics. It was like a mosaic of ancient knowledge building up, all these different pieces.
Different streams feeding into the river. And then, if we fast forward a bit, we get to another really remarkable mind. Archimedes of Syracuse, 3rd century BCE.
Ah, Archimedes.
This is where we see geometry really getting practical, right? Turned into machines, war defenses.
Yeah, he laid the foundations of hydrostatics and statics. His principle of buoyancy, which he detailed in his work on floating bodies, is just a perfect example.
The eureka moment.
That's the one. The famous story, him shouting, "I found it!" supposedly running through the streets after realizing the water displaced matched the object's volume.
Whether it's true or not, it's a great story.
It is. It really illustrates how a pure flash of insight can lead to, incredibly powerful and practical inventions.
So putting this ancient period into perspective,
Yeah.
what's the big takeaway? How did they approach physics, and what were the limitations?
Well, the key thing, I think, is that despite their brilliance, these early works were often really deeply woven into philosophy.
Less about experiment.
Right. Much less about systematic experimental science as we know it now. Aristotle's ideas especially became the main framework. And because there wasn't that rigorous testing, some, let's say, fundamental assumptions just persisted unchallenged for centuries.
Setting the stage for a big shakeup later on.
Exactly. It paved the way for a dramatic, really revolutionary shift that started bubbling up in the European Renaissance.
And that brings us right into the 16th and 17th centuries. Europe's undergoing this profound transformation. It arguably kicks off with Copernicus, right? His heliocentric model.
Yes, the idea that the Earth orbits the sun, hugely radical at the time.
It really set the stage for a whole new way of looking at the cosmos. And then came Galilei,
Yep.
often called the father of modern physics. What made his approach so different?
Galileo's genius, it really lay in his insistence on using experiments in mathematics. That combination was key.
He wasn't just thinking, he was doing.
Precisely. He challenged the old ways. Through his telescope, he made these incredible observations of Jupiter's moons, the phases of Venus.
Which showed not everything orbited Earth.
Exactly. Directly contradicted the old model. And he also did revolutionary experiments on motion. He showed that motion had these universally consistent characteristics that could be described mathematically.
Like the pendulum.
Yes. His observation of a watch pendulum, ticking with that steady rhythm no matter how wide it swung, that was a crucial hint at deeper universal laws.
And the Leaning Tower Pisa story. Dropping the balls.
Probably apocryphal, that specific story. But he did demonstrate through actual experiments that heavier objects don't fall proportionally faster. He directly debunked a centuries-old Aristotelian idea.
So observation and math, that's powerful.
Yeah.
Around the same time, you had Johannes Kepler in Germany figuring out the mathematical laws of planetary motion.
Ellipses, not perfect circles.
Right. Planets trace ellipses, sweep out equal areas in equal times. What's remarkable is how Kepler's laws became a foundation for Newton's later theory of gravity.
Yeah, Kepler really saw the cosmos as this great clockwork governed by geometry. You see that emerging theme of mathematical order.
And this period also had figures like Francis Bacon championing empirical methods.
And René Descartes emphasizing mathematical reasoning. All these threads were kind of converging, leading almost inevitably to Sir Isaac Newton.
And then, boom, 1687. Newton publishes his Principia Mathematica. Monumental.
Absolutely transformative.
It laid out his laws of motion and his law of universal gravitation. We all know the apple story.
Right, the falling apple.
Illustrating gravity isn't just local, it's universal. Pulls the apple, pulls the moon. What was the real breakthrough with Newton?
It wasn't just connecting things, it fundamentally shifted the whole scientific paradigm. Newton's work unified celestial and terrestrial mechanics.
Everything under the same rules.
Exactly. Describing phenomena from falling apples to the grand orbits of planets with these simple, elegant laws, he established mathematics as the universal language of nature.
Kind of the blueprint for physics going forward.
Totally. And he was humble about it, too, famously saying he saw farther by standing on the shoulders of giants.
Acknowledging Galileo, Kepler.
Right. He knew he built on their work. This really marked the climax of classical mechanics, which would dominate scientific thought for centuries.
But even as Newton's system reigned supreme, there were clues, weren't there? Cracks beginning to show, pointing towards something maybe stranger.
There were. And that brings us neatly to James Clerk Maxwell in the 19th century, a brilliant unifier.
Electricity and magnetism.
And optics. He brought them all together. In 1873, he published his treatise on electricity and magnetism. And crucially, he suggested that light itself is an electromagnetic wave.
Which is mind-blowing.
It really is. His equations didn't just unify forces, they predicted radio waves decades before they were found experimentally. Shows the incredible predictive power of mathematical physics.
How did that work, the fields?
He figured out that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. This self-propagating wave, that's light. It laid the groundwork for radio, light, and eventually even relativity.
An amazing achievement.
A true triumph. But, and here's the catch. By the early 20th century, even Maxwell's incredibly successful theories were starting to seem, well, a little undermined. They couldn't quite explain everything. Hints that something fundamental was maybe missing or misunderstood.
Okay, that sets the stage perfectly for the 20th century, a time of genuine revolution. And this is where things get really wild, right?
Oh, yeah. Things take a very strange turn.
It starts around 1900 with Max Planck, a German physicist. He tackled this puzzle about black-body radiation, how hot objects glow.
Yeah, classical physics had a big problem there.
The ultraviolet catastrophe, right?
Right.
Predicting infinite energy, which obviously doesn't happen.
It was absurd. Planck's solution was, well, shocking. He proposed energy isn't continuous, it comes in discrete packets. Quanta.
How profound was that idea? I mean, really.
Incredibly profound. Planck, almost in desperation, introduced this radical hypothesis. Matter emits radiation only in whole number multiples of Newton. Energy equals Planck's constant times frequency.
E equals h nu.
That's the one. The math worked perfectly. But it wasn't just a mathematical trick. It was this deep realization that reality at its most fundamental level might not be smooth and continuous, but, well, chunky.
Grainy.
Exactly. A concept so radical it forced scientists to rethink the very fabric of existence. Planck himself initially thought it might just be a useful trick, but its importance just grew and grew. Einstein later used it brilliantly to explain the photoelectric effect.
And Planck himself. He was quite humble about this huge thing he'd started, and faced a lot of personal tragedy later.
He was, and he did. His discovery wasn't immediately hailed as revolutionary. And tragically, during World War II, Allied bombs destroyed his home, and one of his sons was executed by the Nazis for being part of an anti-Hitler conspiracy.
Oh, terrible.
Awful. Yet he carried on, revered by colleagues, not just for his physics, but for his immense personal integrity. It's a powerful reminder, scientists are human, facing real-world struggles.
Absolutely. Meanwhile, over in Switzerland, a young Albert Einstein was having a pretty good year.
You could say that. 1905, his annus mirabilis, his miracle year.
He published these groundbreaking papers on relativity, Brownian motion, and he introduced the idea of the light quantum, the photon.
Using Planck's idea, yeah.
His special theory of relativity completely changed how we think about time and space. And then by 1915, he developed general relativity, our theory of gravity.
Together, relativity and quantum theory, they basically launched modern physics.
What's amazing is where he did some of this work, right?
Yeah, it's so inspiring.
Yeah.
As a young physicist, he couldn't even get a teaching job. So he was working at the Swiss Patent Office in Bern.
Examining patent applications.
Exactly. And it was in his spare time there that he produced much of his remarkable work. Just goes to show, great ideas can blossom anywhere.
And Einstein's life story, it also shows incredible courage later on.
Definitely. In 1933, when Hitler came to power, Einstein renounced his German citizenship for political reasons. He emigrated to the U.S.
And used his fame for good.
He did. He championed peace, civil rights, and he always saw his achievements not as endpoints, but as stepping stones, always looking for the next question.
So by the middle of the 20th century, physics was just utterly transformed. But the quantum story wasn't finished yet, was it? Others picked up the baton.
Not by a long shot. You had brilliant minds like Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Paul Dirac. They took Planck's and Einstein's quantum ideas and built the full mathematical theory of quantum mechanics.
And what were some of their big, maybe even mind-bending contributions?
Oh, revolutionary stuff. Bohr figured out atoms exist in discrete energy levels. Schrödinger developed the wave equation describing quantum systems.
Wave-particle duality.
Exactly, that waves can act like particles, particles like waves. And then Heisenberg formulated his uncertainty principle in 1932.
Which basically says you can't know everything perfectly.
At the quantum level, yes. You fundamentally cannot know certain pairs of properties, like a particle's exact position and its exact momentum, with absolute certainty at the same time. The more you know one, the less you know the other.
So strange.
It is. And Dirac predicted antimatter, the idea that for every particle, there's an antiparticle with the same mass but opposite charge, which was later found.
It just raises the question, doesn't it?
Mm-hmm.
How can nature be so bizarre at the smallest scales, yet so precise in following these new, weird laws?
That's the mystery and the beauty of it, I suppose.
Okay, so after World War II, physics races forward again. Nuclear physics leads to the atomic age. But you mentioned it also gave insights into cosmic mysteries.
It did, in surprising ways. Think about Hideki Yukawa in Japan. He was thinking about what holds the atomic nucleus together.
The strong force.
Right. In 1935, he theorized that a new particle, which he called a meson, carried this strong force between protons and neutrons. It's an incredibly powerful force over short distances.
And he was right.
He was. His bold prediction was later confirmed when mesons were discovered. It's a great example of theory pointing the way for experiment.
And around that time, you also had Enrico Fermi building the first nuclear reactor.
And exploring particle transmutation, yeah. A very productive era, though obviously overshadowed by the bomb.
And then another really towering figure emerges, Richard Feynman. He helped develop quantum electrodynamics, QED.
Ah, Feynman. A real character and a genius.
His own story is quite something. Started in Far Rockaway, New York.
Yeah, as a kid, apparently he had this amazing knack for engineering, had a lab at home, loved fixing radios.
Tinker King.
Exactly. And his father really encouraged him to question things, to not just accept orthodox ideas. You can just picture little Richard full of curiosity, taking things apart, asking, how does this really work? That was the spark.
And that curiosity stayed with him.
Oh, absolutely. His life seemed to blend playfulness and deep physics. He worked on the Manhattan Project during the war, which he later had mixed feelings about. But later at Caltech, he became famous for his Feynman diagrams.
Little pictures.
Yeah, simple sketches that basically turned incredibly complex quantum math into pictures, made it much more intuitive, accessible even to students learning QED.
And he won a Nobel for that.
For QED, yes, in 1965, shared with Schwinger and Tominaga. And interestingly, the Nobel citation even mentioned his pioneering work in quantum computing thought experiments.
Way back then.
Yeah. He famously said in 1981 that you'd need a quantum computer to properly simulate quantum physics. Talk about foresight.
Incredible. So how do these kinds of breakthroughs lead towards the standard model of particle physics? What even is the Standard Model?
Okay, so the Standard Model is basically our current best theory describing the fundamental particles like electrons, quarks, and the forces that govern how they interact. Except gravity, that's still separate.
The fundamental recipe book for the universe, almost.
Kind of, yeah. And the period from the 1950s to the 1970s saw its development. A key figure here was Murray Gell-Mann.
What did he do?
He came up with a classification scheme for particles called the Eightfold Way. And then he had this incredible realization that particles like protons and neutrons weren't fundamental.
They were made of something smaller.
Exactly. He proposed they were composed of more fundamental building blocks that he whimsically named quarks, a prediction that was later confirmed beautifully by experiments. It's another example of finding simple patterns in what seems like chaos.
Finding the underlying simplicity. And then, in 1979, another big unification step.
Yes. The Nobel Prize that year went to Salam from Pakistan, Sheldon Glashow, and Steven Weinberg.
For what?
For unifying two of the fundamental forces, electromagnetism and the weak nuclear force. They showed they were different aspects of a single force, the electroweak force.
Wow. Salam's personal story is really compelling too, isn't it?
It really is. Born in a rural part of what was then British India, now Pakistan, in 1926. His brilliance was obvious early on.
Cycling story.
That's the one. Age 14, he got the highest marks ever recorded for the matriculation exam at Punjab University. He cycled home from Lahore, and apparently the whole town turned out to celebrate him.
Amazing.
He went on to study at Cambridge, became a major theoretical physicist, and was the first Pakistani and the first scientist from an Islamic country to win a Nobel Prize in science.
And he used his prize money for
scholarships for young Pakistani physicists. Showed incredible humility and dedication to building science back home.
But his life also had significant hardship related to his faith.
Yes, sadly. In 1974, the Pakistani government constitutionally declared his minority Ahmadiyya Muslim community as non-Muslim. It was a decree Salam, a devout member, could not accept.
So he left.
He left Pakistan in protest, continuing his work abroad, but he remained deeply committed to both his science and his faith. He saw them as complementary.
Didn't he quote the Quran in his Nobel speech?
He did. He said, "Our generation has been privileged to glimpse a part of his design, a bounty and a grace for which I render thanks with a humble heart." And famously, he even observed the Ramadan fast during the Nobel banquet week.
A man of deep conviction, clearly. So fast forward to today. Physicists are standing on all these giants' shoulders. We've found the Higgs boson.
The particle associated with the field that gives other particles mass? Yeah, a huge confirmation of the Standard Model.
And we've observed gravitational waves, ripples in space-time, just like Einstein predicted.
Direct detection, another amazing confirmation. But
Yeah.
what are the big questions that still keep physicists up at night? Oh, there are plenty. One of the biggest for sure is the mystery of dark matter.
The invisible stuff.
Exactly. It goes back to Fritz Zwicky in 1933. He was looking at galaxy clusters and realized the visible stars and gas weren't nearly massive enough to hold the clusters together gravitationally. He coined the term Dunkel Materie dark matter.
And later confirmed by others.
Yes. Decades later, Vera Rubin's work on galaxy rotation curves provided really strong evidence. Galaxies spin as if they're embedded in these massive invisible halos of dark matter.
And we now think it outweighs normal matter significantly.
By about 5 to 1. It makes up most of the matter in the universe, yet we still don't know what it is.
That's kind of amazing.
It is. We know it interacts via gravity and maybe the weak force, but it doesn't seem to interact with light, which is why we can't see it. Directly detecting a dark matter particle is one of the biggest goals in physics today.
So how does all this cutting-edge physics connect to our future? We hear about quantum mechanics powering new technologies, even AI.
Absolutely. The connection between physics and AI is actually getting deeper and deeper.
How so?
Well, think about this. The 2024 Nobel Prize in Physics went to pioneers of neural networks. That's an AI method inspired partly by the brain, but also by ideas from statistical physics.
So physics-inspired AI.
And now AI is helping physics. Ellen Moons from the Nobel Committee specifically mentioned how physicists use artificial neural networks, for instance, to help develop new materials with desired properties.
And quantum computing, that goes back to Feynman.
Right, his foresight.
Yeah.
Now teams are actually building processors based on qubits, using quantum phenomena to hopefully solve problems that are just impossible for classical computers.
It sounds like a virtuous cycle.
It really is. Physicists use machine learning, a type of AI, to sift through huge data sets from experiments, design better detectors, optimize telescopes.
And AI research benefits from physics ideas.
Yeah, ideas from physics about complex systems, phase transitions, statistical mechanics. They influence how AI researchers think about things like deep learning. It's a really fruitful cross-pollination.
So looking ahead, the frontiers seem wide open.
Incredibly so. Quantum computing, new experiments, probing for things like extra dimensions or supersymmetry, bigger telescopes and colliders, searching for those elusive dark matter particles. The spirit of inquiry, that fundamental human drive to understand, it's as strong as ever.
It's been quite a journey we've traced. From those early philosophical questions to incredibly precise experiments, ancient geometries to quantum fields.
The constant thread through it all, hasn't it been human curiosity?
Absolutely. That desire to know why and how.
When you think about the key figures we mentioned, Aristotle, Galileo, Newton, Maxwell, Planck, Einstein, Feynman, Salam, Gell-Mann, they were all driven by that deep sense of wonder.
And their personal stories make it real. Salam cycling home in triumph.
Planck enduring such awful tragedy.
Feynman tinkering away in his childhood lab.
It reminds us that science is a human endeavor, full of passion, struggle, and breakthroughs.
Well, we really hope this deep dive has, enriched your mind and maybe sparked some curiosity. Physics isn't just equations on a blackboard.
Not at all.
It's this grand story of people, dreamers, rebels, maybe even poets of nature, constantly asking why and how.
And the story definitely continues. Maybe you, listening right now, will be part of that next chapter.
Could be.
Perhaps probing dark matter, or bending light with new kinds of lasers, or maybe just sharing the sheer joy of discovery with the next generation.
So keep questioning, keep wondering.
Absolutely.
And remember, in the end, the universe is best explored with curiosity.